Hello, my name is Andrew Zulu. Welcome to this presentation on three-dimensional force system or special force systems. We will cover the following: representation of a force in 3D, force along a line in space, resultants, moments, and couples, moments with the vector approach, moments with the algebraic approach, moments about an arbitrary axis, and then we'll look at two examples. Let's get started. So the force representation for 3D is such that the in vector components of the orthogonal system using the right-handed coordinate system, this is what we have here. This is the force F. This component in the x is Fx, which can be written with a scalar Fx times r, which is the basis vector in the x direction, and it's the angle that it makes with the force F is theta x. And similarly in the y, this is Fy with the angle theta y, and similarly also this is the Fz with the angle theta z. So we can say that Fx is F cos theta x, and then Fy is F cos theta y, and Fz is F cos theta z. And if we want to get the magnitude of F, then it's obviously the Pythagoras of these scalars, Fx squared plus Fy squared plus Fz squared square root. Now we can write F also as a vector as follows. We're going to say F is Fx the scalar times I plus Fy the scalar times j plus Fz the scalar times k, for which you can also say, since Fx is F cos theta x, then you can write it like this: F is I cos theta x times I cos theta x in brackets plus j cos theta y plus k cos theta z. Now, if you assign the letter L to cos theta x, and the letter M to cos theta y, and the letter N to cos theta z, then we get the following here. Now, these L, M, N are called direction cosine. So L is the direction cosine in the x, and M is the direction cosine in the y, and N is the direction cosine in the z. It can be shown that cos theta squared cos theta x squared plus cos theta squared theta y plus cos theta squared theta z is equal to 1. So now let's look at the general force along a line in space. Okay, so it will be something like this. So we have a line in space A and defined by the 2 points A and B. The coordinates of A is x1, y1, y1 and z1, and B is x2, y2 and z2, which means that the vector AB, okay, we're going to say is x2 minus x1 times I, y2 minus y1 times j, and z2 minus z1 times k, which means the unit vector along AB is the vector that we just said divided by its magnitude, of which the magnitude is simply these differences of x2, x1 squared, as you see at the bottom here. So this is called normalizing the vector. So the force along the line AB will obviously be FAB, the scalar, times the unit vector in the direction AB. So it's FAB times what we just saw now here. Okay, now if we want to get the dot product of FAB, okay, with a unit vector in an arbitrary direction n, then this is what we do. Now this is going to be useful in terms of how to get the moment of the force about a particular direction. So now F is written as follows. We have seen this before. And then N is written in general. Its N is alpha I plus beta j plus gamma k, which means F dot N, FAB dot N in this direction is simply F, and then L times alpha plus beta times M, and then times gamma times N. So that's our representation of the dot product. Resultants in 3D is similarly described like in 2D. So the resultant of forces F1, F2, and F3 is simply the vector sum of these forces, which is the summation of f, where the x component of that vector sum Rx is simply summation of f in the x and similarly in the y and also in the z. The magnitude of R is simply the Pythagoras of the three scalars Rx, Ry, and Rz. And then the moment about the line, the x-axis, in this case, is R cross f of all the quantities that make this moment in the x, and then R cross f in the y is the moment in the y, and similarly R cross f in the z is the moment in the z, and then the magnitude of the moment vector is the Pythagoras of the scalars mx, my, and mz. Now let's use the vector approach to do this sort of thing. So we've got our 3D force system here. So m is R cross f, okay, just like in 2D. And then what we're going to do is, in this R cross f, we define it with a determinant. So we have ijk, and then R is rxi plus ryj plus rzk. So what we do to calculate the cross product in this case, we say I and then ryfz minus fyrz. And then minus j, because it's a checkerboard pattern, plus minus j rxfz minus fxrz, or if you do say plus j, then you must reverse it, and then you say fxrz minus rxfz, and then plus k rxfy minus fxry, and this is what you see right here. So it's counterclockwise positive in our right-hand coordinate system if we're using vectors. Now let's use the algebraic approach. So in the algebraic approach, we have this system here. This is our force F. It's got components Fx, Fy, and Fz. Okay, we are taking the moment of this force F about this point O here. And then the vector from O to A is this R here. But what we have to do in the algebraic approach is to split this R into its components Rx, Ry, and Rz, and then calculate the moment. So mx, which is the moment about this x, will be due to Fy and Fz, because Fx won't have any moment in the x because it's parallel. Okay, but mx in this case will be, if we take counterclockwise positive and we remain consistent with this throughout our calculation, then we're going to say it's equal to Fz, this Fz here, times Ry minus Rz times Fy. And that's what we see here. And then my, if we look in this direction here, okay, it's going to be fx, this fx, times rz minus fz, okay, times ry. So remember also that in this case, the fy will have no moment in the y direction because it's parallel. And similarly, it can be shown also that mz will be rxfy minus ryfz. Okay, the principle of moments in 3D works the same way like in 2D. We have r cross f1 plus r cross f2 plus r cross f3. So this is the moment vector multiplied by various forces. Okay, this will be the same as r cross f1 plus f2 plus f3 and so on, which is r times the summation of all the forces. Okay, so that will be the moment about a particular point A in 3D. You do it in a similar manner that you do in 2 dimensions. Couples in 3D are treated in the same way. Moment about O is RA cross F plus RB cross minus F. Okay, and this gives us RA minus RB cross F. Okay, now RA cross minus RB is simply R, so this is R cross F. So the definition will be the same as that we see in 2 dimensions. Moments about an arbitrary axis. Now obviously we won't be able to only calculate moments only in the x, y, and z. We could calculate moments about an axis that is not one of these orthogonal axes. So for example, this force F here, okay, we want to calculate the moment of this force, okay, about this arbitrary axis N. So how do we do that? So this is the equivalent of getting the moment of this force about the point A, and then you dot it with the unit vector in the direction F. And that's what you see here. So it's MA. What you're really doing is you calculate MA, and then you dot it with the unit vector that's going in the direction N. Let's see how to do this. So this will be, so MA is simply R cross F, and then we dot it with N. So as a vector, it will be R cross F dot N in the direction of N. But as a scalar, it will simply be R cross F dot N. And we see that the R cross F is a vector. A vector dotted with another vector gives you a scalar. So this is the triple scalar product. Okay, and then how to represent it? We have Rx, okay, I plus Ryj plus Rzk. Okay, that's the first term in the determinant. And then similarly for Fx, Fy, and Fz. And then the unit vector in the direction of N is given as alpha I plus beta j plus gamma k. So we do this cross product here, and this gives us the moment of the about this arbitrary axis, which is N. Let's take an example. So calculate the moment about each of the axes X, Y, and Z, and the combined moment about all of the force couple system that we see right now. So Mx, so the moment about this X, okay, we see that this is parallel, there's no moment. So the moment will be as a result of the 120, the 80, and the 100, and also this 50 here. Okay, so we're going to say if we take counterclockwise as positive, 120 times these two here, minus this 100 times 3, minus plus 80 times 3, minus this 50 here, and that gives us 100 Newton meters, which is counterclockwise. And then My, we see that in the Y, the moment will only be due to this 120, because the 100 is parallel to the Y, the 80 is parallel to the Y, the 150 is going through the Y-axis. So our moment in the Y is simply 120 times 4, which is 480 in the counterclockwise direction. Then our moment in the Z, we see that the 100 is going through the Z-axis, no moment. The 120 is parallel to the Z-axis, no moment. So the moment will only be due to the this 150 here and the 80. So it will be 80 times 4 plus the 150 times these two here, which gives us 620 Newton meters. And then the overall moment about the position O will be the Pythagoras of these things. So it's 130 squared plus 480 squared plus 620 squared, which gives us 795. If we're using a vector approach on this problem, our moment about O will simply be written as 130I plus 480J plus 620K in Newton meters. Let's take a second example. Determine the moment of the force P about the line GE. So this is now a moment upon an arbitrary axis where P is 100 newtons. So we're taking the moment of this about this line here. Let's see how to do this. So the first thing is we ought to calculate the distance from anywhere on the line of action of this of this line to the point P. Okay, and then we taken this point EA, so it will be something like 3I minus 4J. This is what we see here. And then the vector AD, obviously what we want to do is to represent the force in P as a vector. So the vector AD is minus 3I, okay, plus 4J plus 2K, and that's what we see right here. So P as a vector will be this very vector divided by its magnitude, okay, and then multiplied by 100, because we are told it's 100 Newton meters. So this is a unit vector multiplied by the scalar 100, and we get this expression here. And then we have to get the unit vector in the direction GE, okay, so GE is minus 3I, okay, minus 2K, and then we divide by its magnitude, which would be minus 3 squared plus minus 2 squared, and we get minus 3I minus 2K divided by root 13. So the moment of P about the line GE will be R cross P dot NGE. So R is this one, 3I minus J, and then P is this one, which is this, and then we cross it with this vector here. So we get this determinant times the scaling factors that are multiplying these vectors, and then we get our final answer as 123.6 Newton meters. That's it for this segment. In this video, we have shown how to represent a force in 3 dimensions in general, and how to represent a force along a line in space in particular. We have done resultants, moments, and couples in 3D, and then we have representations of moments in 3D using the algebraic and also the vector approaches. We have also looked at moments about an arbitrary axis, and we have looked at some examples. Thank you for your kind attention.